P is the amount of heat required to raise the temperature of a unit mass of a substance while keeping the pressure constant. Under constant pressure, part of the heat energy goes into doing work to expand the system, and part goes into increasing internal energy. C subscript to P is typically greater than C subscript to B because it includes the energy needed for expansion work.
The unit of specific heat capacity in the International System of Units, SI, is joules per kilogram per Kelvin. The equation used to calculate specific heat capacity is C is equals to Q over M delta T, where Q is the amount of heat added in joules, M is the mass of the substance in kilograms, delta T is the change in temperature in Celsius or Kelvin. This formula is derived from the relationship between thermal energy and temperature change, emphasizing how the specific heat capacity moderates this relationship.
The relationship between molecular structure and specific heat, it is because the heat is distributed among a larger number of particles, resulting a smaller temperature change for a given amount of heat, or specific heat, depends on the material's molecular structure, and also the bonding. Substances with stronger molecular bonds typically have higher specific heat because more energy is required to increase their temperature. Another important factor is molecular weight. Substances with higher molecular weights tends to have lower specific heats per unit mass. This is because heavier molecules require more energy to achieve the same change in temperature as lighter ones, but the energy per unit mass added doesn't increase as much. As a result, specific heats per kilogram tends to decrease with the increasing molecular mass.
In conclusion, internal energy, enthalpy, and specific heats are key properties that describe a system's energy, content, and how it changes. Internal energy represents total energy of a system, while enthalpy considers internal energy plus the product of pressure and volume, especially useful in open system. Specific heats quantify the amount of heat needed to raise the temperature of a substance, crucial for understanding heat transfer and energy conservation.
So now let's proceed to another chapter, which is the chapter 4, entitled The First Law of Thermodynamics. The first law, thermodynamics for control mass undergoing cyclic process. The first law of thermodynamics is based on the conservation principles. It gives the mathematical expressions for the effect of the interactions between the system and surrounding on the stored energy or the total energy of the system. In closed system or control mass, interactions can take place only in the form of energy transfer or work transfer and heat transfer. Therefore, the first law of thermodynamics for a control mass can be explained with reference to conservation of energy only. Whereas in an open system or control volume, interactions can take place both by the mass transfer and energy transfer. Hence, the first law of thermodynamics for a control volume is explained with reference to both mass conservation and energy conservation. Control mass or closed system is a system in which energy transfer can take place but mass transfer cannot. Hence, conservation of mass for a control mass can be stated as total mass of a control mass always remains constant. It is dm is equals to 0. For any process between state 1 and 2, m2 minus m1 is equals to 0, m2 is equals to m1. In terms rate, dm and d2 is equals to 0. The change in total energy of a control mass is equal to the heat supplied to the control mass minus the work produced by the control mass. dEAT minus EW. In terms rate, dE and dt is equals to Q minus W. For any process 1 and 2 between state 1 and 2, E minus EQW. Substituting expressions for total energy. U plus PE plus KE is equals to Q minus W, or U plus mgz plus m2 minus 10. Most common example of a control mass is a piston cylinder device, and for a stationary piston cylinder device, the changes in potential energy and kinetic energy are negligible in comparison to the change in internal energy. Therefore, for the piston cylinder devices, UUQ W12. It can also be rearranged for the heat transfer, as a process is said to be cyclic process if the initial state of the system is restored by a number of different processes in series. For a cyclic process, initial and final states are identical, or it is called the delta V. Taking cyclic integral for a cyclic process, then the above equation reduces to, it can also be expressed in the equivalent form as, whenever a control mass is taken through a cycle, then the heat transferred to the control mass is equal to the net work done by the control mass. Whenever a control mass is taken through cycle, then the OR, heat rejected by the control mass, is equal to the net work done on the control mass.
In conclusion, the first law of thermodynamics, which states that energy cannot be created or destroyed, only transformed, is expressed for a closed control mass system as delta U is equals to Q minus W, delta U equals Q minus W, where delta U is the change in internal energy, QQQ is heat added to the system, and WW is work done by the system. In a cyclic process involving a control mass, the system returns to its initial state. So the net change in internal energy over the cycle is 0. Consequently, the net heat added equals to net work done. Q is equals to WQ is equals to WQ, which is a foundational principle in the operation of heat engine and the other cyclic thermodynamic devices.